right, get your homework out here and we'll take a look at a couple of them and see if you got some other ones you want to look at. All right, so yesterday we were talking about this thing called implicit differentiation. And implicit differentiation is when you have a relation, not necessarily a function. This would be, I think this is kind of a slanted, a rotated ellipse kind of a drawing. So you get types of graphs that are not functions, okay? But they still have slopes. They still have y primes. They still have tangent lines. We need to be able to find the y primes on them. All right, and so once you get the hang of this, it's pretty easy. We'll be doing it a number of times throughout the year. It'll be a variety of different times this will pop up. And if you guys are like every other class I've had, you will say, oh yeah, that's where you do implicit differentiation, and then we'll do it, and it'll be fun, right? And we'll get it, okay? So, but it's a mixture of the input and output variables. What we realized is when we say do the derivative with respect to x, that's important. When I first was saying it, you probably thought, why does he keep saying that? It's a big deal. When you do the derivative with respect to the input variable with respect to x, you just follow these rules, right? Was anybody else gone yesterday? Thank you. Okay, so with respect to x, but then what about the output variable? We're doing it with respect to the input variable, so what do? Well, it turns out we do exactly the same derivative rule that we normally would do, but we tack on a y prime. And the reason for that is the output, if we think of it as the f of x, then this would be like doing f of x cubed. Well, we bring the 3 down in front, we would leave the f of x alone, this would be squared, and then we tack on an f prime, because that's a chain rule. Well, if that's a y, if that's y cubed, it's the same thing. So it'd be 3y squared, and then y prime. So we just tack on the y prime when we're doing the output variable. So we just do the normal derivative, and then we tack on the y prime. Okay, so where we run into trouble with these is one like this, for example. We don't recognize that that needs a product rule right there because it's two functions times together. It's negative x times y. So we have to do a product rule. And I would say attach that negative to the x is most helpful. So here's what it looks like. Derivative of x squared is 2x. We do a product rule here. So derivative of negative x is negative 1 with the y left alone. So we get that. Plus, but I didn't write the plus because I knew a minus might be coming. So plus negative x left alone, and then the derivative of y. Now the derivative of y is y prime. Makes sense. But also the derivative of y is 1, tack on a y prime. Just like derivative of x is 1, right? Derivative of y is 1, tack on a y prime. So it's just 1 y prime or y prime. Plus the derivative of y squared is 2y, tack on a y prime. And then the derivative of 1 is 0. Make sure you don't forget that, because a lot of times people put a 1 there and then that throws off their answer. Derivative of 1 is 0. So we're doing the derivative of both sides. All right, now we want to group our y prime terms together on one side. So I left those here. I moved those over. It would be possible to do the reverse of that. It'd be possible to move the y primes over. If you do, your answer will look different, but I'll know it's the same when I grade it. Okay, I'll show you that in a minute. Okay, the only difference will be instead of getting like 3/9, well, you're going to have x's and y's, but this is just to give you what would happen. You'll get negative 3 over negative 9. You'll get the same thing. It'll just be, it'll look different, right? But they're equivalent. Okay, so anyway, we keep the y primes on one side. We factor out a y prime, and then we divide that quantity over there. Now, if I would have put it on the other side, it would have looked like this. Okay, but they're the same. Because look, if I take a negative 1 out of here, I get 2x minus y. And I take a negative 1 out of the bottom, I get x minus 2y. And then the negatives cancel, and then I get that. So either one of those will be accepted. And I'll just follow your work and all that. Okay? Very likely one like that will be on, at least one like that will be on the data. Okay? All right? Involving some sort of product rule, something like that. Okay, I got another one here. I got 21. If you want to see another one other than this, we can do it. But I just thought I'd pick out a couple here. Okay, so now we got this one. Now this one's a little tougher. And the directions are weird. The directions say find the equation of the tangent line. Okay, well we could See, that question I can throw in anytime. Find the equation of tangent line. What do you need? Slope and a point. Slope and a point. They give you the point. So all you need is a slope, which is y prime. So you need to find y prime, right? So it's the same thing you were just doing on those other questions. We need to find y prime. Then we'll plug in our 1 and our 2. We'll get our slope. Then we'll have our equation of our tangent. Okay? All right. Because all we need a point. With the equation of the line, we need a point, and we need a slope. Okay? I already got the 1 and the 2. All I need is a slope. I need the y prime. So here I go. So I got this 2 sitting here. It'll hang out. I got a 2 out squared, so I'm going to bring the 2 down. So I'm going to bring the 2 down. That makes 4. I'm going to leave the inside alone. So we just do the same stuff. I'm going to leave the inside alone. So there's no y primes yet. I haven't done anything to any y's yet. Okay? Leave the inside alone. There'll be a 1, which I won't write. And then I got to do the derivative of the inside. So I put parentheses. What's the derivative of the inside? X squared, derivative is 2x, plus y squared is 2y, y prime. Okay? Whenever I do the derivative of a y, do it like normal, tack on a y. Over here, I'm going to do a product rule. Now, I think the smart thing is to attach the 25 to the x. Just put those together. Okay? So the derivative of 25x is 25. Leave the y alone. Plus, leave the 25x alone. Derivative of y is 1. Tack on a y prime. Or just the derivative of y is y prime. Everyone think. Sometimes, for whatever reason, people want to put y prime when they do the derivative of y. That's not what you do. Right? The derivative of y is 1. Tack on a y prime. All right. So I got that. Now, this one's a little trickier because we said we need to get the y primes together. Well, if you need that, like on the last problem, it was easy because we just had a whole bunch of terms written down here. We could move the terms around. So what are we going to, unfortunately, what are we going to have to do here? What are we going to have to do? We're going to have to FOIL this out. We're going to have to FOIL this out and get a bunch of terms written down so we can take our y prime terms and get it together. It's our only option. Okay? So this one's a little messy. So I'm going to put that 4 inside there first. I'm going to put that 4 inside there so it's not just hanging around out there. Okay, so I'm going to put the 4 inside that one. And then now I'm going to FOIL those. So I got first, I got outer, I got inner, I got last. Okay, so what do I got? 4x squared times 2x is 8x cubed. Outers be 8x squared y prime. Inners 8xy squared. Last times last 8y cubed y prime. And then over here I still got that. Okay, now I got 3 terms that have y primes on. Right? I got one here, I got one here, I got one over here. So I got to get those all on one side. So 2 of them are on the left, so let me move that other one over to the left. Let's move these other 8s here, there, and there. Let's move those over to the other side. Okay? And so it looks like that. So I got my 3 y prime terms over on the left, got my non-y prime terms on the other side. Okay? Now I ran out of room here, so I'm going to skip a step. But I would take out the y prime, and then I would divide by what's left. Okay, so I took out the y prime, and then I divided it, and I got that. But we're not done on this problem because they wanted the equation of the tangent line, right? And so what do we got to do? Got to put a 1 in for each x, got to put a 2 in for each y. And I did that over here, and I think I got 2 11ths. So 2 11ths is my slope. Now it dawns on me that I actually would not have had to go all the way down to here to do this problem. But if you did, I'm glad you did, because that's what you need to practice for next week. Okay? Plan on Tuesday for the quiz. Wednesday, the problem with Wednesday is it's a short day, so we only have an hour. An hour should be plenty of time. If you know what you're doing at all, if you have any chance probably of getting 8 out of 10, you should definitely be done in an hour. If you're still working after an hour, then I don't know. Maybe you just got off track of a bunch and now you're fixing them, whatever. So it might be better to have more time. Okay, so I think we can be ready by Tuesday. Kind of depends how much practice you do between now and then, because after today we have nothing new to do. Okay, we have nothing new to do but practice. we really needed for this problem is to get the 2 11ths, right? We needed to plug the 1 and the 2 in. We could have done that way back here, right? We could have taken the 1 and put it in for all the x's. We could have put the 2 in for all the y's, and the only thing left would have been our y primes, and then we could have just solved for y prime. So we could have done that if that's all we really cared about was getting the 2 11ths, which is what they asked in this problem. But I think it's good to do this because this is what you have to do in the quiz. I'm not going to ask you to do this other thing. I'm just going to ask you to find y prime. So you're going to do that. Okay? Now that would be a really hard one. So we talked about the gateway test having some easy and some medium and some hard, right? And so this would be in the hard, just because it's got so many places you can make a mistake, right? But this one would be medium. I mean, this one we should be able to do, right? It's got that product rule in it, so you got to mess with that. Right? I wouldn't put it in the easy category, I guess, but it's, you know, you got to be able to do it. All right, this one would be a little beyond probably what we'll do, unless I decide, hey, one of the hard ones I'm going to make be this. But okay. Remember, you missed 2. You missed 2, you can still get it. All right. What else? Anything else on that page with the implicit? And you can make these up all day long, especially these guys. You know, and you can do a sine of y or an e to the y, right? E to the y, the derivative is e to the y times y prime. Sine of y is cosine of y times y prime, right? What's sine of y squared? What's a derivative of sine of y squared? Cosine y squared, 2y times y prime. Right? Yeah. Normal derivatives, like you would normally do everything the way you normally do, and at the end, when you do the derivative of the y, tack on the y prime. When you did the sine, you weren't doing derivative of y, you were doing derivative of sine. Right? It's cosine, leave the y squared alone. Then the derivative of y squared is 2y. Right? So stuff like that. So again, you can just make them up. You know, make this an x squared and an x and a y cubed or something, right? And just put some numbers in front here. Make that a plus, whatever. You just make some up and practice. Okay? And I'll look at them for you if you want me to. Because we don't have a lot of good practice problems other than these in the website that had some on it. Maybe I'll do a search for implicit differentiation practice or something. And you could too, right? And see if you find something. But anyway. All right, anything on page 195? Any of those? And if you do any on the website, and of course on the websites you have a chance to see the answers. They'll tell you what the answer is. You can type in your calculator to see if you got it, whatever. But if you're still not sure, or you think, hey, this would be a good one to show everybody or whatever, write it down, and then when I give you a chance to do this, like on Monday especially, you know, so we can talk about it. Okay? But any on 195? Yeah. Are there answers on 195? Yeah, I think so. What is that, section 3.5?
Oh,
yeah.
It's just 3.5.
Yeah, it's section, page 195 is section 3.5. So yeah, they're in here. They're in here, so you can take a picture of that. Yeah. Okay, any that you tried on page 195 that you wondered about or think would be good ones to look at? Now this is our chance. 6. ln, now I'm going to rewrite these to be honest. I like how they use different letters because we could do the derivative with respect to z or u or x or whatever, it doesn't matter. But I'm just going to give them to y'all as x because that's just one less thing you have to worry about right now. But then it's pi times sine what? E to the z, which would be x. Okay, I'll just make that x. Okay, so I'm just going to write like that. Okay, which you can too when you're practicing these because that's how I'm going to give them to you. Now remember, pi is just a number, right? So pi is just hanging out there in front of that. So we're not going. There's no product rule to do there or anything, right? And this is not a product. This is ln of that stuff, right? So we're going to start by doing what? 1 over. So we go to our rule here. We go to our rule sheet, and ln u, the rule is 1 over u times u prime, right? So ln u, ln of some stuff, is 1 over that stuff times the derivative of that stuff, the derivative of that. So now I'm just looking at the red part. Probably put it myself, set of parentheses here, just to double check, but it turns out I'm not going to need them. But, and so what do I do to do this? Well, the pi said just going to hang out there. What's the derivative of sine? Cosine is a 3-step process, right? So I'm down. So here I was doing the derivative of the outside, so the derivative of ln is 1 over, so that's step 1. Step 2 is leave the inside alone, which by putting that there, that's what I was doing, was leaving the inside alone. Okay, some people think they got to write the inside down again to leave the inside alone. No, it's 1 over the inside. So right there, by putting that was step 2. That was leaving the inside alone. Now I'm doing step 3, derivative of the inside. Well, when I do the derivative of the inside, I got a pi, and it's got its own inside. So step 1, derivative of sine's cosine, leave the inside alone, times derivative of its inside, which is that right there. Derivative of e to the x is e to the x. Now, as I step back and look at this, I don't have any powers on the outside. I don't have any plus signs anywhere. So it's really just a bunch of things multiplied together, and I got this. So, is there any simplifying it? I can stick this up on top. And anything else? Cancel those, right? For sure, I got to cancel those pi's. Now, yes, that is cotangent, but I don't care. That's fine. Write it cotangent, but you can leave it, right? Some people think simplifying is actually, it's better to put things into sines and cosines because we're just more familiar with those. So some people would rather them be cosine. So if you had cotangent, they'd almost rather make it cosine sine. So I don't care either way. But then I would just stop right there, right? Nothing cancels. Don't try to cancel those e to the x's. My God, you can't do that. It's on the inside of the function, so that's not possible. But the pi's definitely need to cancel, right? You could just cancel them back here like that. That would have been okay, right? You don't have to move this up on top, okay? If you'd have just done this and done this, I'd have been fine with that answer. Okay? But it looks a little better having that, okay? And if it were me and I was getting graded on a gateway test, I'd probably rewrite it and make it look nice, but, you know, kind of depends on time as well. Okay? All right, what else? Y equals e to the x squared, so I put that in parentheses, times tangent of what? Cube root. Now, as soon as I saw that cube root and I was writing it down, I would rewrite it as this. If it was a gateway test, it was on paper, I would still rewrite it before I did anything. Okay, so it would look like that to start. Okay, so at the beginning, what are we using this problem? Right, there's a lot of stuff inside. I see all that. But where do we start here with what? What root? This is product root. This is product root, right? We got one thing times another thing. So this is a u prime v plus uv prime, right? So, you know, I remember Vanessa asked the other day about, you know, how do we know what rule to start with, whatever, and it's just the way the problem was. So on the last problem, it was a chain rule, because the last problem was not a product. It was a function with some stuff inside it. So we started with the ln rule, okay? And then, of course, the chain rule. The chain rule is a part of just about every problem, right? Almost everything has some stuff inside it, okay? So this is a product rule. So we got our u and we got our v. So here we go. So we got y prime would be the derivative of this. So I just ignore everything else and I'm just focused on the u prime part. So what's the derivative of e to the x squared? E to the x squared times, no, 2x. Derivative of the inside, right? So e to the x squared. What's the rule for e to the u, e to the u, e to some stuff, e to the u? It's e to the u times u prime. So e to the u, the derivative is e to the u times u prime. Right? Now that u I'm talking about right now is different than that u, so just so you understand. But it's, right, you just tack on the derivative of the inside. So all I've done is u prime. So now I got to tack on the v, which is this left alone. Right? So I did the derivative of that. And now I tack on that left alone. Plus, e to the x squared left alone. Now I put those parentheses around that squared. They didn't, but I think they should be there. I think it makes it easier to see this is the inside kind of thing. So I leave this alone. Now I'm ready to do the derivative of tangent. So now I'm all the way over to here. Now I'm doing v prime. So now I'm just focused on this. So derivative of tangent. Well, again, this is one of those we got to learn. Now, if you look at this rule sheet, the other day we learned product quotient, then we learned the chain rule. Those are there. All these other rules we already had, all the way down to sine and cosine. We already had all those. So the 4 other trig ones you just need to memorize are right here. So you need to memorize those. Okay, that's why I put stars by them. The ones I put stars by are the reason I put stars by them was, these are the ones you probably need to look at a little bit just to make sure to memorize. The rest of them, I think we've used so much, you just know them already. Okay, so that's why I put the stars by them. Those are ones you might want to just look at a little more. Okay, so those 4 trig ones, okay, so they were in the book, and now they're on here, so you just got to memorize it. And then today we're going to learn those last 3. Okay? All right, so what's the derivative of tangent? Secant squared. And we can use our lazy notation. We leave the inside alone, x to the 1/3. And then we got times by the derivative of that, right? Derivative inside, which is 1/3 negative 2/3. Now, again, this is, so remember yesterday I said, if you are constantly trying to simplify and rearrange and, oh God, how am I supposed to write this? If you're doing that on every problem, you're doing it too much. You're doing it too much. Like this one, you're done. Stop. Now you can rearrange some things, but there's nothing to put together. So now again, I key in on the plus sign. So to me, this is like one big thing right here. Okay, and then this is one big thing right here. Okay, so I look at this and I say, what can I do? Well, I can move the 2 and the x around. That's fine, but that's just rearranging. Okay, here I can move this around front, but it's just rearranging. Now, if I had another number here, like a 4, then yeah, the 4 and the 2 I need to put together, make an 8. Somebody asked about a negative. What if you had a negative here and a 2 here? Yeah, you should put those together, because to me that's a -1 and then a 2. That needs to go together to make -2. Okay? But that x doesn't have to come over here. I mean, that's just rearranging. So I can just stop. Okay? And I think I also said when you have a mixture of function families like this, a lot of times that's when you're just done. You know, if you got some x's and stuff, like we did on number 21 today, you got to FOIL it out and move some things around. It's a little different problem, but still. Okay, this one we had to cancel by, you know. All right, what else? Anything else? We got about 5 more minutes here before we need to do the next thing maybe. So if you got another one. There you go. Maybe see if you get your test right now. Sure? Nobody? Page 195? Did you do 10 of them? If you did the first 10. Now, again, you maybe skip around a little bit, you know, because they probably get a little harder. But not really. They're kind of mixed around in there. Make sure you get some that are quotient rule. You get some that are product rule. Make sure you get some that are, you know, stuff on the inside, that kind of thing. Okay. All right. So a lot of your assignment's going to be practice. Now I want to take about 20 minutes of your time here and do some inverse trig stuff because we've got to talk about these inverse trig. Okay. And I think it's important time. I think it's valuable information. It's not all real valuable for next Tuesday gateway. Okay. You just got to memorize the rules for that. But I think it's important. I think we need to do it. There's a little bit of homework on it because just longer term, knowing the trig stuff is important, and it's going to help us review that. Okay? But aside from doing that piece of homework, practice, 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 practice. Monday should be mostly about just cleaning up and getting, you know, a few questions answered so that you can then practice some more and be ready to go. Again, probably plan on Tuesday is the way I'm leaning right now, because you got a weekend, you got a Monday. Now with people that are in play production, that squeezes in a little bit, but maybe they'll do theirs the next day. We'll see. But anyway, all right. Well, okay. So I'm going to talk about inverse functions here a little bit. Now I say we're going to take about 15 minutes, maybe 20 here to talk about this. Now, how much of this you write down, I don't care. It's up to you. It's more some long-term thing. What I want to do is I want to lead us to how this, we're going to focus on arc sine. I'm going to lead us to how this derivative rule comes about. It is kind of a weird one. I mean, because sine, all the other trig functions have trig derivatives. Why do the inverse trig functions have these square roots and stuff in it? Why does that happen? That's what I want us to get to. And along the way, we're going to review some things about inverse functions. Okay? That are going to come in handy later down the road. So how much you need to take notes on, I don't know. That's up to you. The first part maybe a little bit with some of the trig stuff. Okay? All right. So inverse functions. So a little bit of a pet peeve of mine is this idea of inverse. When I ask you what's the inverse of 2, and it's not your fault, it's math teacher's fault, the other math teacher. When I ask you the inverse of 2, what do you think? Negative 1/2. If I say the inverse of 2, you think negative 1/2. Okay, that's fine. That's what I'm asking. What do you think? Anybody else think something different? Just 1/2. That's the more common answer I get. You've kind of combined 2 inverses to get negative 1/2. And this is my pet peeve. And again, it's not your fault. If I ask you what's the inverse of 2, what your response should be is which inverse do you talk? Which inverse do you mean? Okay. The multiplicative inverse of 2 is 1/2. The reciprocal. The additive inverse of 2 is negative 2. Right? We usually call that opposite. Those are 2 different things. Okay? So most people, when they think of what my experience has been, when I ask what's the inverse, they think reciprocal. They always think reciprocal is an inverse. But that is an inverse. It's not the inverse, right? There are a lot of inverses. So you have multiplicative inverses, which is reciprocal. You have additive inverses, which is opposites. And we have function inverses. Now, they all kind of mean opposite, right? They all kind of mean undo each other kind of thing. But what we're talking about are function inverses. Now, unfortunately, when it comes to the trig functions, we've made it really hard on ourselves. I just hate this notation, and I'm never going to use it with the trig functions. I hate that notation because what's it make you think of? It makes you think of 1 over sine, but that's not what it is, because 1 over sine is cosecant. Another function, that's not the inverse function of sine. Cosecant's not. It makes you think of 1 over sine, but it's not. It's inverse sine. So what I'm always going to do is write arc sine for my inverse function of sine. Now, unfortunately, we have no other notation if we just want to talk about the inverse of f. We have to do f negative 1. Again, that makes you think 1 over. It makes you think reciprocal, but it's not. It's not. It's just notation we use. It's unfortunate notation. I wish we had something better, but nobody's come up with anything, and I haven't either, so I guess I shouldn't complain. All right. Anyway, so let's talk about a couple of inverse functions. Okay, so first of all, let's talk about square root and square. Okay, now what you probably remember about inverse functions, again, you can write some of this down, you don't have to, whatever. But I just want to quickly go through some things about inverse functions. You probably remember from last year, hopefully, it's about interchanging the x and the y. Okay, we interchange the x and the y. So if I'm going to take y equals x squared, which is this parabola, if I interchange the x and the y, I get x equals y squared, I do the square root of both sides, I get plus or minus square root of x. Right? That's a sideways parabola. You might also remember that when we interchange the x and the y, that's equivalent to doing a mirror image around this. Right? So we get that. That's all. Okay? But we get a mirror image in the y equals x line when we interchange the x and the y. Okay? So that's some of what you already know about inverses. Okay? Now that's going to come in handy again later on. Okay? Now what about, well, I don't know how you know this, so you're trying to write it down. Okay? So we also have E and ln are inverses. They undo each other, right? Y equals e to the x, there's the graph. So if we interchange the x and the y, we get x equals e to the y. But then we want to solve for y. So we do the ln of both sides. ln x, ln e to the y, bring the y down in front, ln e is 1. we get y equals ln x. So we interchange the x and y, so we can see that ln x and e are inverses of each other. Okay, they undo each other. Okay, now one of the things I mentioned a while back, and I'm sure I just mentioned it in passing, so it didn't mean much to you. You probably didn't think about it. I said that inverse functions undo each other, except with some possible domain issues. Okay, and that's something we're going to talk about here a little bit, because the trig values definitely do have some domain issues. Okay, so does x and x squared. Now, ln x and e to the x don't. But anyway, so here's your y equals x line, here's your y equals x line. So again, we can see mirror images. Mirror images. All right, so one of the facts of inverse functions then is that they undo each other. So this is what this means. If I do ln of e to the x, I get x. If I do e to the ln x, I get x. No domain issues. Those are always true. Now, the reason there's no domain issues is e to the x, the y's are always positive. And so in ln x, the x's are always positive. Right? And so we have no problems. Okay? But with square root, we do. Square root, they kind of undo each other. Okay? Well, let me tell you what I mean. This one actually does work. Okay? So this one is actually true. If I put a 3 in, or if I put a 9 in here for x, right? What's the square root of 9? Okay, now I tricked you. I tricked you. You were right when you said 3. You were wrong when you changed it to plus or minus 3. Okay, so let me talk about that real quick. Okay, if I ask you to solve this equation, what's your answer? Plus or minus 3. Because I'm asking you what values work for x. So you do the square root of both sides, but you got to tack on a plus or minus. But if I ask you, what is the square root of 9? Your answer is 3. Just 3, right? It's called the principal square root. Just 3. If I want the other one and I put a negative on there, then that's negative 3. So there's two different questions. So if I ask you what's the square root of 9, you give me 3. The square root function as a function remembers the top half of the parabola. We only get one answer out. Okay, so two different questions. They're easily confused, and I understand, and I tricked you there into changing your answer. Okay, but on this one, so let's come back to this. So I put a 9 in here. What's the square root of 9? 3. Square it, 9. So I started with a 9, got a 9 out. Now, what if I put a negative 9 in there? Oh, I can't. Okay, I can't. So this will always work, because I can't even put a negative in. Okay, now, let's go over to here, and let's reverse it. Put a 3 in here. 3 squared is 9, square root of 9 is 3. So I started with 3, and I got 3 out. But let's start with negative 3. Is it legal to start with negative 3 here? Sure. What's negative 3 squared? 9. What's square root of 9? 3. Do I get the same thing now that I started with? No. Now, I get its opposite. So if you type this into your calculator, it'll tell you absolute value of x. Okay, so if you ask it to do the square root of x squared, you're expecting it to say x. It's going to say absolute value of x. That's because you can't get a negative out of a square root, but you could have put a negative in. Okay, so it'll give you that. Okay, so that's what I mean by domain issues. That's what I mean by domain issues. So basically, square root and x squared undo each other, kind of, but there's some domain issues. That's what I'm talking about. All right, so now let's get into the sine function. Okay, this is kind of a long trip, and it seems like where is he going with this? Remember, where we're going to end up is right here with this derivative rule. That's where we're going to end up. But if I just tried to go right to that, it would really be confusing. So I'm trying to build up to this, okay? So that's where we're going with it. Okay, so I've given you some issues, and so I told you some things about inverse functions and these domain issues and things like that. Okay. So now let's investigate the sine function. There's a graph. If I was to do the inverse of that, of course we know that it would be a mirror image. Well, it's going to be, so like these things would be reflected, and so it's going to look like, it's going to come in here and go, did I do that right? I might have done that wrong. I might have went the other way. I think I was supposed to go the other way. Oh well, you get the idea. Okay, it would look like that. Well, that's clearly not a function, right? That's clearly not a function. It's kind of like square root of x. If I draw the inverse of x squared, it's not a function. So what we have to do is we have to restrict it. We have to restrict it to just the top half. So it's a function. Well, we're going to have to do the same thing here with our inverse of sine. Okay, now I always like to think of sine as I put angles in, okay, pi 6, pi halves, and I get values out between -1 and 1, like square root of 2 over 2, square root of 3 over 2, 1/2, right? I get those kind of values out of the sine function, and I put angles in. Now, why do I care about that? Because what am I about to do? I'm about to interchange the x and the y. So when I interchange the x and the y, I got to understand, these are angles that are going in, right? It's always angles that go in, and it's values that come out. So now my values, so now my x is going to be the -1 to 1s, and my y's are going to be the angles, right? Because I've switched them. Okay, now how do we undo this? And I'm setting you up for failure, so I'm not even going to let you answer. Because what I used to do is I'd say, how do we get the y by itself? And then somebody would always say, divide by sine. That's awful, right? We're not dividing by sine because that's not a times, right? What do we do to both sides to get y by itself? We do the inverse sine, right? We just do the inverse sine. Well, what is that? Well, I'm going to call it arc sine, right? I'm going to call it arc sine, not sine -1. We could. It's arc sine. Okay? In your calculator, they use that sine -1 notation. So the way we get the y by itself is we do the inverse sine of both sides. Now, understand, remember, x is our values from -1 to 1. And these out here are angles, right? The y's are angles, like pi6. So what we get out of arc sine is angles. Coach Harris, anybody know Coach Harris? Riley Harris, he used to be the football coach here for a long time, and he taught honors advanced math forever. He's a legend. He's not only a football legend, he's a math legend. But anyway, and I mean, I'm not joking, I'm serious. He's unbelievable. But anyway, there was a time when Tom Osborne came to, you've probably heard that story. Tom Osborne came to the high school. He was recruiting one of our players. And they called down to his class, and he was in the middle of a lecture, much like what I'm doing now. They called down to his class and said, hey, Coach Harris, Coach Osborne's here to see you for your appointment. He says, tell him I'll be there in 20 minutes when I'm done teaching. And he just kept running. Kept Coach Osborne waiting. Okay, I love that show. All right, so anyway, his class was probably disappointed, but whatever. All right, so arc sine of x, here's what he would always say, and I still remember this. When you see arc sine, here's what you should say. It means the angle whose sine is x. So if I ask you for the arc sine, which I'm going to do in a minute, the arc sine of 1/2, if I ask you for the arc sine of 1/2, what you say to yourself is the angle whose sine is 1/2. The angle whose sine is 1/2. Okay, which we'll get to in a second. All right? But anyway, that's the arc sine function, and here's what the graph would look like, but we have to restrict it. We have to restrict it or else we'd get this thing, and that's not a function. So where do we restrict it? Restrict it, because we want to get all those angles where we're only going to restrict it from -pi-halves to pi-halves. In other words, this quadrant and this quadrant, first and fourth quadrants, because that'll give me my positive values and my negative values. Okay? First quadrant will be positive, fourth quadrant will be negative for sine. Okay? Cosine we would restrict to 1 and 2, positive and negative, so 0 to pi. Okay? But that's not a big deal right now. I mean, it's a little bit of a deal, you know, just reviewing some trig stuff, but that's what we do with inverse trig functions. So if I ask you the question, what's the arc sine of 1/2? Thank you, Coach Harris. He would say the angle whose sine is 1/2. What is that? What's the angle whose sine is 1/2? Pi over 6. That's the answer to that. Now, hang on a second. Is that the only angle whose sine is 1/2? What's another one? 5 pi 6. And 13 pi 6. Right? And 17 pi 6. And I can go on and on. There's an infinite number. But remember, this is a function, so we only want one value. That's why we restrict it to only these two quadrants. So if you type into your calculator arc sine of 1/2, it will say pi 6. Okay? It's only going to give you that one. So, okay, now remember, we're getting there. We're almost there, right? We're going to get to this derivative rule in a second. What if I ask for the arc sine of 3/5? Again, this was some stuff you did in honors advanced math last year. Arc sine of 3/5. That would be the angle whose sine is 3/5. Well, that's not any one we've memorized, so this is one we could draw a triangle. Remember SOHCAHTOA? The angle whose sine is 3/5. Sine is opposite over hypotenuse. Right? So that picture, I don't know what that angle is, and I'm not even going to write anything down, but that would be the angle whose sine is 3/5. Right? That angle right there. Okay. So, where do we go from there? Well then, this was the next question that you would have had this last year. What's the cosine of the arc sine of 3/5? Well, you would start on the inside. You would say the angle whose sine is 3/5. So then we draw a little triangle. Here's the angle whose sine is 3/5. And then we want the cosine of that. Well, cosine's adjacent over hypotenuse. Well, how do we get this adjacent leg? Pythagorean theorem. Well, you already know that, right? That's a 3, 4, 5, right? That's going to be 4. So it's going to be 25 minus 9 is 16, square root is 4. So that's 4. So what's the cosine of that angle? 4/5. And that's your answer. 4/5. So you start in here. The angle whose sine is 3/5 would be this angle right here. And then we want the cosine of that. Be 4/5. Okay? All right. So we're getting there. We're getting closer. All right? So what if I said to you, what's the arc sine? Now notice I've reversed them now. Which one I have where? Right? Kind of like we did square root of x squared or x squared and then the square root, whatever. We've reversed them, but let's talk about this. So what's the answer to this? Remember we said how inverses undo each other? So if you do a sine and an arc sine, what should you get out? It's the same you started with. But remember we said there's some domain issues. There's some domain issues. So let's before we put pi 6, let's convince ourselves. So what's sine of pi 6? Sine of pi 6 is 1/2. What's the arc sine of 1/2? Oh, remember we were restricting to here and here. It's pi 6. Oh yeah, so it worked fine. Okay, but what about this? What's the sine of 5 pi 6? Also 1/2. What's the arc sine of 1/2? Pi 6. Because we don't look in this quadrant, we look over here. So sine of 5 pi 6 is 1/2. What's the arc sine of 1/2? We just said that's pi 6. That's what I mean by domain issues. Domain issues, right? So for the inverse, when you do the inverse, you don't always get out what you had put in because of domain issues. Okay, so it's all coming together now. Well, not quite, but we're getting close. One last fact. Let's bring calculus in, because so far we haven't done any calculus yet in this whole 12 minutes we've been going. Okay? Seems like a lot longer now. We haven't brought any calculus into this, so let's bring in the derivative. Let's bring in slope. So I got two functions that are inverses. I got x squared and square root of x. They're inverses. I call these partner points. So on x squared, you got the point 0.39. On square root, you got the point 0.93. Okay? They're partner points. Okay, now, they're not at the same point, right? Because one's got an x of 3, one's got an x of 9. So if I want to do the slope of this parabola right here, I do the derivative, get 2x, put in a 3, I get 6. Seems reasonable. It's pretty steep. Seems reasonable. Now let's do this one. Square root of x, x to the 1/2. Do the derivative. Flip that down to the bottom. Plug in the partner point. Now I'm not going to plug in a 3. Over here I plugged in a 3, but over here I'm going to plug in a 9 because the x, y are switched. Right? So I'm plugging in a 9. Square root of 9 is 3. 2 times 3 is 6. 1, 6. Seems reasonable. It's pretty flat. Now think about inverses. They're mirror images. When this gets real steep, its mirror image is going to get less steep, right? Is this a coincidence that those are reciprocals? It's not. The derivatives of inverses are reciprocals. The derivatives of inverses are reciprocals. Okay, now. Okay? But at the partner point. So on this one, it's the derivative at 3. On that one, it's the derivative at 9. Okay? So that brings a whole other issue into that later on we'll see. So remember I said long term a little bit here? So later on, we'll come back and revisit this and say, hey, remember when we talked about reciprocals? Not opposite reciprocals, but just reciprocals. Okay? Both positive slopes. Okay, so as that one gets steeper, that one's going to get less steep. All right, so now we bring that idea of the derivative in. Okay, now we're ready to go. All right, now we're ready to go. So, now, and to be honest, I'm not sure you have to write the rest of this, what we're going to do here, because we really don't care what we get right now. But we're going to bring in, so all the stuff we just talked about now all comes together. So sine of arc sine of x should be x. Okay, should be what we put in. Now, if I say, what about the domain issues you talked about? Well, it turns out the domain issues are only when we go the other way, right? If we flip these around, then we've got domain issues. This way we don't have domain issues, right? Because what's this going to be? This is going to be arc sine of some value between -1 and 1. So if this is arc sine of square root of 2 over 2, that's pi force. What's the sine of pi force? Square root of 2 over 2. We're always going to get what we put back. So when we go this way, it's kind of like that x squared. One way it worked all the time. The other way we had domain issues. Same thing here. When we go this way, no domain issues. So this is a true statement. Okay? Now, let's do the derivative of both sides. Okay? So let's do the derivative of both sides. Well, on this side, derivative of x is just going to be 1. Let's do the derivative of this. Well, we start on the outside. What's the derivative of sine? Cosine. Leave the inside alone. Times the derivative of arc sine. We don't know the derivative of arc sine. That's what we're trying to find. So I'm just going to call it arc sine prime. Okay? So let me do that again. Derivative of this, start on the outside. Derivative of sine is cosine. Leave the inside alone. Times the derivative of arc sine. I don't know what the derivative of arc sine is. That's what I'm trying to find. Okay, so I'll just call it arc sine prime. Equals 1. Now let's divide the cosine over. Okay? So now let's divide the cosine over there. And we got this. Now we don't want to mess with that. We can do something with this right here, but we're getting close. So the derivative of arc sine is this. Okay? All right. So derivative of arc sine is this right here. Now, Coach Harris would say that this is the angle whose sine is x. The angle whose sine is x. Wouldn't that be that picture right there? Isn't that the angle whose sine is x? Right? Opposite over hypotenuse. The angle whose sine is x. Okay? Do some Pythagorean theorem to that. 1 squared equals x squared plus unknown side squared. 1 minus x squared equals unknown side squared. Unknown side would be the square root of 1 minus x squared. Would you agree with that? So the unknown side is that. And so this triangle is the angle whose sine is x. And now we want to do the cosine of that. Remember we did 4/5 a minute ago? What's the cosine of that picture? This over 1, adjacent over hypotenuse. So the bottom here is just that. Right? The whole bottom would just be that. Now look at your rule. Okay, there it is. Okay. We got it. All right. So I think there was some value in what we did. Long term, there's some value in what we did there with inverse and just understanding inverse functions and stuff like that. There's going to be some homework assignment in 3.4 that deals with some trig stuff, but that's always good to review. So we want to do that. But the most important thing for the short term is this rule. So look at our cosine. It's the same except what? It's got a negative on top. What about our tangent? No square root. It's got a plus sign. Just got to memorize that. Okay? So for the gateway test, what will the gateway test look like? The gateway test will simply be y equals arc sine of 3x to the 4th. Okay? Something like this. Okay? What's the derivative of arc sine 3x to the 4th? Go. Now don't look up here if you don't want to see it. Now, probably not going to make you do, the bottom part, right? 3x. I mean, you know, you could argue, well, isn't that doing 3 times 3, and so squaring that is 9? Probably not. You know, leave it like it. Now, rarely, never really are you going to be able to square root that, so you're not really ever going to be able to simplify that bottom thing to the point where you could then cancel or whatever. So most of the time when you do one of these, you're just done. You could put the 12x cubed up on top. That's fine, right? But it's 1 minus x squared. What it really means is 1 minus u squared. So whatever's on the inside here is what's gonna go in there and get squared. And then you're gonna do the derivative of the inside. So they're real easy to use as far as doing the derivative, right? They're real easy to use. They're just like the other rules. You just memorize them and then you just plug them in correctly, okay? So they're easy to use. All right. So 3.4, next line was a 3.4 homework. So that's going to be some of the trig stuff. And then a lot of practice on page 195. Get on those websites if you want. But again, you can get a lot of practice in just doing 195. Okay. So practice. 10 problems a day. What's that? 30 problems by Monday. I mean, you do 10, do 5. I don't care. You want to take 7 gateways? Go ahead. But you want to pass it the first time, right? So get going. Get a lot of practice in, be ready to go. Be overconfident. Practice until you get 10 in a row multiple times, right? You only need 8, but you can always, often you can count on making one dumb mistake, you know, with getting a negative sign or doing something like that, right? Or something silly. Maybe 2 of those, right? If you do 1 of those and then 1 you just don't know how to do, you know, then you're kind of close. All right, so the rest of the time's work time. Finish up the playlist we had going last period.
Is this fire yesterday's?
I don't know.
I am not the kind of girl who
That's what Strachan recommended.
on a white veil occasion, but
He was singing.
I'm not the kind of boy who should be marrying a
Scarier thing is why I have this in my library.
I sneak in and see your friends and her snotty little family all dressed in pastel, and she is yelling